The last video, I left off where we were talking about, well, we were wrapping up the whole idea about what the utility and how PCA can be used. And then I said, I'm going to go into an example. And the example really kind of clarifies one singular point, which is that PCA results in orthogonal components, and it does away with multicollinearity by definition. So I'm going to begin by just going through an example where, suppose what I wanted to do is predict the total scores that were generated by the International Olympic Committee, these scores for the heptathlon. And what I'm going to do is use the scores that are computed by that formula as my dependent variable, and then use the individual events as my predictors. And as you'll see here, that all of the events are significant predictors of the total score, except for hurdles. Hurdles fails to meet the 0.5 level. So and for those of you who are familiar with this, you can take a look, and these are the variance inflation factors. It's not a great presentation of them, but you can see exactly what they are. And 11.5 for hurdles and 12.7 for long jump. Those are pretty high values. I don't use cut scores for these types of things, but I look at the variance inflation factor along with the fact that the p-value is greater than 0.05, and immediately you should start thinking, whoa, okay, multicollinearity is probably in a non-trivial effect here, that it's suppressing the results. So one thing that we can do is we can create a principal component analysis result and use all 7 of these events to create a first principal component, or maybe multiple principal components up to 7, and use those as predictors, and VIF will then all go to 1 because they're all orthogonal. So that's one of the advantages of using PCA. Let me give you another example that kind of works on both sides of the regression. And this is kind of a silly example, but it's an example that does clearly show what PCA is doing here. So if we have 3 crimes, murder, assault, and rape, and then we want to know whether urban population is somehow or another related to crime, we can use PCA. We can use a variety of tools, but PCA turns out to offer some unique advantages. So we've got 3 crimes. We've got 50 states, plus I believe we've got, maybe do we have the District of Columbia? Oh, maybe not. So we've got 50 observations. We've got 3 crimes, and we've got urban population. So we could look at the problem as urban population causes crime. But many of you will quickly realize that in multiple regression and correlation, or MRC, it's not really suitable for 3 dependent variables. We could run 3 bivariate models, but that's not exactly telling us what we want to know. So one thing we can do is we can flip the model around, and we can use the 3 crimes to predict urban population. So you'll see here, this is the regression results for using those 3 crimes as predictors of urban population. I know that seems a little odd, but this is the model that we would be testing: murder, assault, and rape, all causing or predicting urban, and I wish I had spelled that correctly, urban population. So here you'll also see in the regression model results, you'll see that murder is a non-significant and assault is a non-significant predictor, and only rape predicts urban population. So one thing that we can do is we can perhaps look at the correlation matrix among the 3 crimes, and you'll see murder and assault are correlated 80, murder and rape are 56, and assault and rape are 67. So you've got 80, 60, and 70 correlations. Those are pretty high. And when I look at the variance inflation factor results for my model, you can see that murder, assault, and rape all have pretty high VIFs. Pretty high meaning that they're high enough, they're sufficiently higher than 1, and it's clear that they're not significant. 2 of them are above the P of 0.05 level, and we only have 1 significant predictor. So PCA is a useful device, tool here in this case, to be able to reduce our three crimes into principal components. And by reducing them into orthogonal principal components, we can then use them in a way that either as predictors, three principal components predicting urban population, because we know that they're going to be independent, or what we can do is we can flip the model around and we can say, I really just wanted crime, and I'll use the first principal component as my dependent variable and urban population as my predictor. So you'll see here, these are the results. Remember that in R, it produces standard deviation and not variance. So if you just take this 1.54, square it, you'll get the variance. And we have a maximum of 3 for variance. And you'll see that this is 80% of the variance for the first principal component. And if you see the A weights, the A weights indicate that it's pretty much all just crime, general crime, murder, assault, and rape, all fairly equally weighted, okay? If we move down to the scree plot, you'll see now we've got variances, and we know we have a maximum of 3, and look at this. It's about 2.5, almost 2.4 for the variances for the first principal component, and you'll see here there's a really steep drop-off where principal component 2 and 3 are below any threshold. So the first principal component really captures the variance that we're interested in, 80% of the crime variances. If we use the 3 principal components as predictors of the urban population, you'll see the first principal component, which is general crime probably, is a significant predictor. And then PCA2, let's see what PCA2 is. It looks like it's largely rape and minimizes. Remember, since these are all negative here, that means it values these guys. And then it values this guy more so than the others. So the second principal component is rape. And so we have general crime and rape as both 2 significant predictors of urban population. Now that seems a little weird because here we've got PCA 1, 2, and 3 all predicting a misspelled urban population. Sorry about that. But let's flip it around and let's have urban population be a predictor of the first principal component. And now we have a model where it's a little bit more logical that crime is the resultant of population density, and we have a significant predictor. I view 0.05. I would just report that as P equals 0.05, but it looks like urban population is a significant predictor of general crime. Okay, and this is what the resultant model looks like. We have urban population, and then we have general crime. This is the first principal component, and the greater the urban population, the lower the crime. But that's not true, because if you look at the A weights are all negative. So therefore, what's happening is the parameter, or our PCA, is lower values are actually more crime. Okay, so let's take a look at Dunteman again. We're coming full circle. We reviewed Dunteman the first half, and now this is the second half. And I want to give you some of the details of this. So first, PCA is a data reduction strategy. We use PCA just like we use any other scoring method to reduce lots of variables into fewer ones. PCA is widely used across many fields beyond just social and behavioral sciences. The whole aim for PCA is to reduce the data, but it's to explain the most variance in the original variables. Okay. PCA is not a measurement model. It's purely driven by the data, and it's a linear, it's a weighted linear sum of your standardized variables. And you can see here Y is the principal component, A is our weights, and X's are our original variables that are now standardized. And the more simplified formula is right here. Y1 equals the summation of the A weights times the X's. Remember that the X's are standardized. Now, this model is difficult to estimate without some constraints, because there are more unknowns than knowns. And we learned when we were in grade school that that's a problem when we're solving simultaneous equations. So we have to have some constraint, and the constraint that we have in principal component models is the sum of the A weights, these weights that we're using to calculate the scores, the sum of these squared weights for each principal component must equal 1. Okay, so that's what it looks like under the hood. We're not going over any of the linear algebra, but there are plenty of resources available, which I'll post on the website. One of the advantages of PCA, as I said before, is that PCA residualizes each subsequent component. So therefore, all of the principal components are orthogonal or independent. And we saw that before when we looked at what the results were for the correlation matrix among the principal component scores. It's an identity matrix. There are ones in the diagonal and zeros in the off diagonal. Finally, PCA results depend upon the variances. Remember, PCA is about variance. And when we start out with variables, original variables that have substantially different variances, the variables with the most variance win. They contribute the most to what goes into the principal component score. So majority of principal component analyses as implemented in software, they only use standardized values. So standardized values, mean of 0 and a standard deviation of 1, therefore a variance of 1, and it homogenizes the variance, therefore taking away that opportunity for any of the more variable variables, meaning the variables with the most variance don't now somehow or another swamp the model and take over. Now every variable gets equal treatment. Okay, now that's a very brief summary. I recommend that you read Dunteman, because without reading it, a lot of these summaries are just they're not sufficient. All right, now I want to move on to some points about PCA not covered in the readings, and these assumptions are somewhat critical, but in other cases they're kind of brushed away because of what PCA does to the data ahead of time. So one is linearity. All relationships in principal components must be rectilinear, but they need to be linear in the sense that principal component scores are added. And so linearity refers mostly to pluses, but in this case we also refer to rectilinearity, meaning that the relationship among the variables and also the relationship between any variable and the principal component must be summarizable by a straight line. In other words, we don't want curvilinear relationships. We don't want complex relationships. We want things that can be expressed in bivariate regressions or correlations. Next is normality. Because PCA is a normal distribution theory model, it works on measures of central tendency, means, and measures of dispersion, variances. That the mean, remember, is the best guess. And our uncertainty about the best guess is the variance. And if we look at variance and the mean, so both measure of central tendency and measure of dispersion, and we don't know what the distribution is, then those two values are not terribly informative. So therefore, we need a model, a distribution model that sits underlying this procedure that we can have some faith exists. And that model, that distributional model, is the normal distribution. Normal distribution theory is part of PCA. PCA relies on it. Next is sphericity. The great part about PCA is because it standardizes all the variables have roughly the same variability. They have it by definition. The final assumption is one that becomes the greatest lightning rod for people turning away PCA, because what they say is PCA is not a useful procedure because it demands that all of our original variables are measured without error. When I hear people say that, I usually assume that they don't know the assumptions of regression, because regression, multiple regression, and correlation make that same assumption, that all variables must be measured without error. Why is this the case? Well, both regression and PCA demand a lot from the data. And the parameters that we estimate are basically parameters that don't take into consideration measurement error. Because they don't take into consideration measurement error, we have to either know what the measurement error is, or we have to assume it to be 0. And assuming it to be 0 is the easiest assumption. We also know that this is a convenient fiction in social and behavioral sciences. Most of our original observed data contains error, and because it contains error, we need to spend some time attending to the fact that that assumption is not likely to be tenable. Okay, those assumptions aside, we're going to talk about them in a little bit. The other thing I want to talk about is the distinction between components and factors. So I showed you earlier something that clearly delineated a factor in my advanced organizer. So I have a factor that causes V1, V2, and V3. These variables, 1 through 3, are manifest variables, and they're manifestations of an underlying entity, a factor. That model is not the model that we test in principal components. A principal component is an emergent property. It emerges from the existence of our data, much like a regression parameter, except in regression, our dependent variable is observed. In principal components, it's not observed. It's inferred based upon the data. So the model for components looks like the second figure, where a principal component is defined by and caused by those 3 manifest variables. And incidentally, the principal component, notice it doesn't have a circle around it. This is standard SEM or causal model figuring. So the principal component is a rectangle, and that means that principal components are are observed. They're computed directly from V1 through V3. Okay, now, because the measurement model is such that, well, the factor model is a measurement model. Principal component is nothing more than a brute force model. Now, some people may argue that it is a measurement model, but I would say that what it is it's a model that's purely dependent and driven solely by your data, which means that, as far as I'm concerned, there's not much of a model. There's not much of a model to generalize to. So these assumptions that I talked about before, they're relevant for both factor analytic models and principal component models, and we'll talk about that in exploratory factor analysis later. Okay, so that concludes these lecture notes. These lecture notes that we just went through are the, let me get to the top of it. This is the first lecture, and I'm going to transition over to the next lecture in the next Hangout. So stay tuned for that.